Okay, welcome to your Chapter 13 introductory video. This is chemical kinetics. Kinetics is just really basically a fancy word for rates, or if you will, speeds of reactions. Here are your learning goals. You gain an understanding of rate expressions and laws. You really get familiar with a lot of terminology, things like orders and rate constants. You'll need to be able to look at a data set and from that determine orders and rate constants. We'll spend a lot of time talking about the integrated first order rate equation, and you're going to look at several orders. You're going to look at zero order, first order, second order. The first order one is the only one you're really going to need to do a lot of calculations for. The others we'll look at conceptually. We'll calculate half-lives, and that will pertain only to first order rate laws once again. And then ultimately we'll look at temperature effects and how that affects rates. And the last thing in your chapter is mechanisms, including intermediates and catalysts. And mechanisms really mean what's happening at a molecular level. We're going to look at, really explaining what's going on. Okay, first thing in your chapter, one of the first early things in your chapter is this idea of relative rates. And I want you to look at this expression. Now, there's just a balanced stoichiometric equation. And I want you to really look at how the rates of the reactants and products would compare to each other. So what you can imagine now here, we can talk about the change in the concentration of nitrogen. We use delta for change. So you're going to look at the change in the concentration of nitrogen as a function of time. Okay? And my question to you is how that relates to oxygen. Well, you might look at this and say, okay, well, if N2 is going to disappear, it's disappearing because it's forming NO. And therefore, oxygen also is disappearing. And because they're in a relationship of 1 to 1, it becomes very clear that the concentration of oxygen then should be exactly, the rate of oxygen disappearance should be exactly the same as the rate of nitrogen disappearance. Because these molecules have to come together, react to form NO, so they should disappear at the same rate. We often put a negative sign out front because it's disappearing. The question then becomes, how does that relate to the change in the NO? And you can see that obviously the concentration of the stoichiometric coefficient for NO here is, of course, 2. And therefore, 2 molecules of NO must form for every one of the N2 and O2 that disappear. So really, NO's rate is twice as fast, right? We're going to form 2 NO for every 1 N2 we lose in a given amount of time. So you might think you want to put a 2 up here, but remember, this is an equal sign here. So effectively, we then have to say, okay, for this rate, which is twice as fast, to be equal to these, the 2, the 2 has to go down here. Now, since this is twice as fast, if we've divided by 2, it's going to be equal to this rate. And of course, we don't put a negative sign here because this one is increasing. So this is the early part of your chapter, just getting a good, thorough conceptual understanding of how to relate the rates of reactants to products, the rates of disappearance and formation. Now, we've mentioned equilibrium in general chemistry more than once, and it's going to be a major topic in Gen Chem 2. And this graph is meant to show you the concentration of the reactants versus the concentration of the products over time. And it very clearly shows you now what equilibrium really means. And equilibrium is reached when the concentrations stop changing, if you will. So maybe right about here, we reach equilibrium. There's no longer a change in concentration. What is happening here is the forward rate, the forward rate, which I'll call rate sub F, is equal to the reverse rate of the reaction. The rates are now equal. So initially, when this reaction first starts, we see obviously we have no products initially. The reactants are decreasing, right? The products start to increase. You can imagine the rate of this will start to decrease. This is not a graph of rate, it's a graph of concentration versus time. So you can see the rate starts to decrease. Well, you're getting less and less now of your reactants present. Therefore, less collisions, okay? And therefore, the rate of the forward reaction is slowing down while the rate of the reverse reaction is increasing. And this, the concentration of the products is increasing, so that rate is increasing. Eventually, the two rates become equal. The concentration of the products and the reactants do not change after that point because the rates are equal. It's important to realize that equilibrium is a dynamic process, and that is, it's not like the reaction stops. You're still forming reactant and you're forming product, but it's happening at the same rate. It's also important to realize that the concentrations are not equal necessarily, and that's why this graph is done the way it is. You could theoretically get that rare case where you get something like this, and they actually are at the exact same concentration, but that's just a rare particular case that might happen. That's not the definition of equilibrium. It has nothing to do with the concentrations. It has to do entirely with the rates. And as a result, the concentrations do not change. It's an important concept to get down. There's also average versus instantaneous rate, and I think most people would have an idea of what that is. If I drive to Nashville and it takes me 30 minutes to get there, you can calculate my average rate, but my rate at any given moment in time might be, 75 or 70 miles per hour. That changes. And what you see here is a case where we're looking at comparing the initial rate, if you will, and different instantaneous rates. So these are all instantaneous rates, but this one right here is actually an initial rate. It's the initial, so it's the rate right at the beginning, okay, when the reaction starts. All three of these are instantaneous rates, but that's a specific example of an instantaneous rate right at the beginning of the reaction. So if you've taken calculus, it's the slope of the line that's tangent to the curve that gives you these instantaneous rates here. Okay, that's all there. Now, one of the first things in your chapter that's really important is this idea of reaction orders. And a reaction order, important to realize, this is experimentally determined. Experimentally determined number defining the dependence of the reaction rate on the concentration. So you can imagine different cases, and it'll become more clear as we go through the chapter, but once you really get to the end of the chapter and start to look at mechanisms, then it makes a little bit more sense how you can have different dependence on concentration. So we'll leave it at there. You can just accept for right now that different chemical reactions can have different dependence on concentration. So that's why it needs to be experimentally determined. The rate law is ultimately just an equation you write that includes the concentrations and the orders and a description of that reaction overall. And the overall reaction order is the sum of the exponents for the concentration terms in the rate law. That just becomes easier to look at an actual rate law here than try to picture that in your head, of course. So we have reaction A plus B going to C. Here's my rate law. We say the rate is equal to a rate constant. That's what that is. It's a rate constant times the concentrations A and B. Those are the concentrations of my reacting species. Of course, the assumption here is, okay, we're starting with A and B. We have no C. We're just moving in one direction here. We're measuring that rate. M and N are known as the reaction orders. And there are with respect to each of the particular reactants. So M is the order with respect to A, and N is the order with respect to B. That's just a common, notation people use, M and N, but you can use anything really. And actually, M plus N is what we know as the overall order. And that's what we mentioned back here. The overall order. We're just going to sum those up. It is that simple. So that is your rate law. Now, one thing I need you to spend a little time on is looking at determination of rate laws using initial rates. This is a big section in the chapter. Now, I will tell you this. This is a long chapter. It's very involved. We will not be getting through this chapter in one day. So you can watch the whole video, but focus on the first half of the chapter, and you can go back and watch the second half of the video if you want later again. But I do need to spend some time on this. It's something we will cover most definitely in the first lecture. And that is, if we have an experiment, let's take something very simple you're trying to figure out. You're trying to figure out, okay, what's the problem with your car? And to figure out what's wrong, you basically test one thing at a time. You don't pull out your battery and your alternator. You test the battery first. Because if you do two things at one time, then you can't ever figure out what's going wrong. It's much easier to hold one constant. This whole idea of initial rates, that's what you're doing. We run 3 tests, and we're trying to figure out how the rate depends on our 2 reacting species, which in this case are NO and O2. So in trial 1 and 2 here, we're going to hold the concentration of NO, as you can see, constant. Okay? And we're going to change the concentration of O2. And then we're going to see that the rate changes. But now we can tell, we'll do this in class very closely, take a close look at this. You now know any change in this rate here is directly related to the change in this concentration because this one was kept the same. And then if you look at, if you will, trials 1 and 3, in trials 1 and 3, what we have here is these 2 are held constant. Therefore, this change here that results in a change between these 2, change in rate, is directly related now to the change. Did I do that right? No, that's oxygen. Yes, that's right. So this change here is directly related to the change in NO. We're holding this constant this time. That's the whole idea of initial rates, and we're going to use that as a way to determine rate constants and rate orders, which have to be determined experimentally. It's the whole idea here is you're going to be learning how to conduct an experiment to determine rate constants and orders of reactions. And the reason we do this is because once you determine these, you'll be able to then use this equation to calculate rates at any if you will, any instant during that reaction. You can calculate the concentrations at any time. So I know, hey, I've got a pesticide spill in this particular river. And I've already worked out for that pesticide its reaction rates and its reaction orders and constants in water. We've done that in the lab. So now we can predict how long it's going to take that pesticide to degrade in the water and know, hey, some distance downstream, it's then going to be safe. And the pesticide will have dissipated. So this is the whole reason why you want to get a rate law, is to be able to use that. So you can imagine that the concentration of a reactant affects the rate. That shouldn't be that surprising. You have increased collisions between reactants, leading to faster rates of formation. That's really all I'm going to say about that slide. So the integrated rate law, then, this is a big section. The integrated rate law. So here's a particular data set. It's ozone as a function of time. You notice that is not linear, and this one is actually fairly close to linear, but you see some that are going to be very different. So this is just another approach to get at rate constants as opposed to using initial rates. So what we're going to do is we're going to integrate the first order rate equation. You're going to look at your book very closely with this, but the integrated rate law is simply going to wind up being, and you don't have to know your calculus, it just turns out to be this, and you can, if you know your calculus, look at this a little closer, the natural log of the concentration of the reacting species at any given time is equal to the rate constant negative the rate constant times time plus the natural log of the initial concentration of your reacting species. So if you remember, and if you don't, you need to review this a little bit. And your book does have a section in the back that reviews stuff like this. This is a equation of a straight line. Y equals mx plus b, where my slope here is negative k. I'm going to graph time versus natural log. That's my y and my x. And my intercept then, b, is going to be the natural log of initial concentration. So now what's nice is you simply go in the lab, measure your concentration as a function of time, and from that I can get my rate constant by graphing it in a linear fashion like this. You can also use that first order rate equation, and we can rearrange that and manipulate it to get to what's called half-lives. And half-life is exactly what the word says. It's a time for half of the particular species, whatever you're looking at. In this case, it's N2O, to disappear. So this particular half-life in seconds is 1 second, which means if I start with a concentration of 16 molecules, after 1 second, I have 8. After 2 seconds, I lose half of that 8, so I now have 4. So what you see is the line, as we call this exponential decay, is an exponential curve, is because the amount that's disappearing decreases in each half-life. So the first second you lose 8, the second second you lose 4, the third second you only lose 2. It gets less and less. You can get the idea of this can drag out for quite a long time. That is really half-life, and we'll spend some time on that. Okay, one of the last two major sections in your book for this chapter are reaction rates and temperatures, and then mechanisms. So that's the last two things we're going to look at here. So here's a particular energy profile of a reaction. It's the energy versus the progress of the reaction, or if you will, time. And what you see here is something called the energy of activation, or the activation energy. And it basically is a barrier that the reacting species have to get over to get to form products. You remember from the previous chapter we talked about thermodynamics, spontaneous reactions, and we said things like, hey, you know, this reaction is spontaneous. Methane reacts with oxygen to form CO2 and water. That's a basic combustion reaction. But the reaction has to get started. We have to provide the spark. So that initial energy you have to get over to get the reaction going, that's your activation energy. Okay, and then because this is exothermic, this reaction is exothermic, the reaction of the energy of the reactants is higher than the product, so energy is being given off. This right here literally is your delta H. The enthalpy of that reaction, it's going to be negative. So because it's negative, you've got energy released, then the reaction keeps feeding itself, and it's spontaneous and keeps going. So the energy of activation is that barrier you must overcome. And of course, you know that temperature affects the energy of a reaction. So this is the Arrhenius equation. We're going to spend some time on this in class, but you can basically see that at a higher temperature, we have a greater fraction of molecules that have enough energy to get over kind of that barrier and go to form products. And that's all this curve is showing you here. Okay, the last section in the chapter is reaction mechanisms. And when we say mechanisms, we mean specifically what is happening at a molecular level. You know, I say to you, methane reacts with oxygen to form CO2 and water. Well, that doesn't tell you anything about what's happening at a molecular level. What I mean by that is, okay, do the carbon-hydrogen bonds break first, and then the oxygen bonds break as hydrogen bonds to oxygen, or do these molecules come together and form some sort of complex, and then you start to lose hydrogen and form water? What happens? Okay, so here's some terminology you should get familiar with in your book and learn what those statements mean. But when we have elementary steps, it's a molecular level view of a single process taking place in a chemical reaction. Here you see an overall reaction right here, and here's the observed rate law. What these are here are actually elementary steps, which means they are what is happening at a molecular level. And what we're seeing is that an NO molecule will react with an oxygen molecule to form NO3. We call that an intermediate. That doesn't show up here. That doesn't tell you anything. The balanced chemical reaction doesn't do anything about what is happening on a molecular level. These are elementary steps, what is actually happening on a molecular level. And with elementary steps, you can write a rate law directly from it because it is what's happening at a molecular level. So it's not just a balanced stoichiometric reaction. So you can actually say that the rate is equal to the rate constant, we'll just call it K1 for step 1, times NO times O2. That is the actual rate law. You cannot write a rate law from a balanced stoichiometric reaction. It has to be determined experimentally. That's what we spent the whole beginning of the chapter emphasizing. Using initial rates, using an integrated rate law, okay? And as we go into mechanisms more in class, you'll start to get a better picture of why that is. And simply because you don't know what's happening at a molecular level. So you can go ahead and write the rate law for the second one also. The last thing in your chapter is catalyst. This is pretty straightforward and just requires a little bit of reading. A catalyst is a substance added to a reaction that increases the rate of the reaction but is not consumed in the process. Your body is filled with catalysts called enzymes. Enzymes are proteins, but they're specialized proteins that speed up reactions in your body. Most reactions in your body are catalyzed. They just happen too slow to maintain you as an organism biologically without them being catalyzed. And basically, not consumed is important. It means those enzymes in your body, they catalyze a reaction, they come off the reaction products or whatever, they're bound to the intermediates, they form, complexes, and they come off and then go catalyze another reaction. And basically what they do, and they do it more than one way, and we'll talk about that in class, but they lower the energy of activation. That's what this figure is showing here. And I believe that is the end of the video. And there's a lot of material in this chapter. You're going to need to spend time and, of course, watch this video before we start this material.